Alrighty, so this is the video for the workbook C1.1 enzymes. This is going to be the video for just the SL pages, partially because I'm on a little bit of a time crunch, and partially just because I think it's a nice separation of the packet, because one of them's kind of basics about enzymes, and then the rest is like slightly more detailed information. And so the first thing we look at is enzyme substrate specificity. So all enzymes are specific to their substrate. And so the overall three-dimensional shape of an enzyme's amino acid structure, and it's specifically the structure of its active site, which is where your substrate binds, is what's really going to determine what substrate that this enzyme works with, because it's important that they have a matching active site and matching substrate, and even the portion of the substrate that binds is specific to the active site of that enzyme. And so what your enzyme will do is it binds at that active site, holds on to it, and then what it's able to do is start to weaken those bonds or catalyze the reaction by lowering the activation energy. Reaction occurs at the enzyme, and then boop, it's released and you have your product. And so although this process is kind of like a lock and key, in that it is really specific, the active site on the enzyme itself isn't necessarily like always perfectly built to have that substrate bind. It's not necessarily like a perfect keyhole right away. Like the lock is kind of like a squishy lock hole. Imagine like if you were to put in a key to your lock hole, but then when you put the key in, your lock hole kind of grips onto it or like forms to its shape, almost like if the lock hole had like a lining of Play-Doh. That's like your induced fit model. And this happens because there's different chemical properties involved with your enzyme's active site and your substrate that allow it to kind of form to that specific shape. And that's what's meant when it says the induced fit model. And so to put that ramble into words, let me scooch my little paper up. Beep, beep, beep. And so we'll make the active site orange. Your active sites they are only determined by a few amino acids. If you're wondering like what the rest are, the rest of your amino acids are structural. Which makes sense when we think about it, because remember this blobby is just kind of like a representation to make it easier for us to think about it. Really, it looks like the chain of amino acids linked together by your little your polypeptide bonds, and then you have your amino acids that'll specifically change to be your active site when you have that induced fit. It's not that they change, I guess. It's that they have those specific properties of the active site and they're already in vaguely the right formation, and then they shift slightly. So in here is the active site of your enzyme. I don't have an orange highlighter, so it's just going to be outlined. Sorry. So in here is your active site, and then the specific amino acids that make up that active site, you can see them here. These are the ones that actually chemically bind your substrate. So it's 3, 4, and 5. This one. And then 24, 25, 26, so 1, 2, 3, 24, 25, 26, and then 41, which I think is this one. And so they change shape to be able to meet it, but they already have the correct chemical properties. And so it's like a chemical lock and key, but a structural key and Play-Doh lock It's weird. And so that's kind of where your induced fit model comes in. What color should induced fit be? Purple. So your induced fit model it causes, let's pick a color for enzyme. We'll make enzymes red. We'll make substrates something that's different than red. Teal. It causes your enzymes to change shape when binding occurs. And that's kind of your special induced fit versus your lock and key. And so your active sites are really like the secret to how this happens. So your active sites are very structurally and chemically similar, or not similar, but like paired up with your substrates. Chemical, structural. Active sites, chemically, and structurally is there 2 L's? We're gonna go with 2 L's. Structurally pair with substrates. Oof. And so what we mean by that, structurally, the 3D shape of the active site and substrate lineup, they're like the lock and key ish, knowing that they do this induced fit thing. And then they're also chemically paired so the properties of active sites and substrates attract each other. It's usually due to opposite charges. And so if we look back at our little picture, we see our substrate here. Woo! Woof. Our substrate here, it binds. I don't have a teal highlight. I should have picked highlighter colors for these. Oh well, it's fine. So we have our substrate. We have the active site of our enzyme. It's the active site. And then enzyme in general is the rest. And they're binding because it has those similar chemical and structural properties. So it has the same shape or I guess like matching puzzle piece shape, same structure, match, and chemical attraction. And so they're kind of drawn together here. And then when it goes to the complex, you notice there is a very slight change, but still a change, in this active site because of the induced fit. Oh shoot, I just realized I wrote this in the, oh well, it's fine. Then here's the substrate. Woo! And so the slight change shape, that's your induced fit. And then we see it here too. You have your active site marked. Here's your induced fit. It's a slight change in the position of those active site amino acids. And then we have your substrate. Ooh, oof. Okay, this is why I usually use highlighters. And you have your substrate here, and you can see the reaction has already started to occur. So I guess really it's kind of the substrate slash it's becoming the product, but whatever, it's fine. It's fine. We'll mark our little enzyme amino acids. Boop, 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 boop. As red. Maybe I should have picked more different colors. I was going to say differenter, but more different colors than red and orange. Oh well, it's too late now. So it's not like a crazy change, just a simple one. Okay, good enough. So your induced fit, it's like your lock with a Play-Doh. It's like your regular key with a Play-Doh lock. So regular key, Play-Doh lock. Key is your substrate. Oh, that's the wrong color. Gosh darn it, Jessica. It's okay. It's fine. I'll forgive it. I'm not going to redo this. Key is your substrate. Enzyme is your lock. But it's a slightly different lock. It's Play-Doh-y. Going down, then we look at our stages of our enzyme reaction. And so really these are stages that we've looked at. It's pretty much just the process of binding. And then once it's bound, having that like catalyzation of the reaction that starts to weaken or stress the bonds in your substrate. And then you have your full-on reaction and then your product leave. And so we'll do a rainbow. Red. Oh, it's gonna be kind of a weird rainbow. That's okay. Yellow. And then the next color I have in the rainbow is green. I don't have orange. So first step is your substrate binds to the active site of the enzyme because it's structural and chemical specificity. And that's what we're seeing happening here. Your second step is while your substrates are bound to the active site, bonds in the substrate are stressed or weakened, causing it to change into a different chemical substance or the products of the reaction. that you see in B and C, because in this time, your reaction occurs. And then in step 3, products separate from the active site, leaving it vacant for substrates to bind again. Oh, it's like a traffic light. And so I'm gonna have to use the brown one. Oh well, it's fine. In this case, it's making a polymer. It doesn't always have to be making, it can also be breaking. But in this case, we have substrate 1. This is just like your cut and paste that you did. Substrate 1 bound in. Boop. Substrate 2. This is like the worst bootleg red color. It's fine. Substrate 2. And then it forms your product after that reaction. Whoop. I like using red, blue, and purple because then it shows the combination of the 2 substrates as the product. See? Look at me being cutesy. And then your enzyme, oh, very unfortunate. It's gonna be the brown. Actually, maybe we'll leave the enzyme gray. We'll just color in the active sites. So your active sites are here. Active sites. They're still here. This is more of a lock and key picture because your active site doesn't shift slightly. Not very accurate workbook. It's fine. And so there you go. Those are your 3 steps. Binding, reaction occurring, product releasing. Enzyme can be reused. It can be recycled. We'll put a little recycle symbol. Oh. Okay, maybe not. Not good enough. It can be recycled. Or reused. I guess reused is a better term. That's fine. Okay. On to the next page. Dum-ba-da-dum. Bum-ba-da-dum. Alrighty, so this is when we're talking about molecular arrangements affecting the formation of enzyme substrate complexes. And so while some enzymes are embedded and immobilized within a membrane, most enzymes and their substances are found in solutions in the cytoplasm. And so for a substrate and an active site to come together, molecular movement is needed so that the substances can collide. The greater the kinetic energy of the enzyme and substrate, the greater the chance of collision. When enzymes and substrates are in solutions both doing the movement, they're more likely to have those collisions because they're both moving. When an enzyme is immobilized within a membrane, the substrate has to do all of the movement. And so there are benefits to having immobilized enzymes. Number 1, in cell membranes, your enzymes kind of have to be immobilized because they're working within the membrane. It also makes them able to take in substrates from outside and put the products inside, or vice versa. Immobilized enzymes are also really useful in medicine or in production because your enzymes can be easily removed when production needs to be stopped, versus if it's a free-floating enzyme, it's hard to kind of trap that without having to denature it, which can then, in order to denature it, affect other pieces of that puzzle, because you'd have to change temperature or pH or so forth. Anyway, and so some enzymes, some enzymes are embedded or immobilized within a membrane. Here's your little example in your cell membrane. And remember, when your enzyme is immobilized within a membrane, your substrate is the only thing that's doing all of the movement to cause those collisions. Most enzymes and their substrates are both in solution. Which is their cytoplasm, which is just like an aqueous solution or like a water-based solution. And so most of the time, that movement is really kind of forced because they're constantly moving around in that liquid. And so for a substrate and active site to come together, they do need to have these collisions, like where they actually touch each other. Because remember, although we talk about these things and they're almost personified, these are really just molecules at the end of the day. So just like any other chemical reaction, they have to touch in order for it to happen. So substrate and active site to come together, molecular movement is needed so your substances can collide. And then the reason that temperature can increase, which I guess we'll talk about in a second, but the reason that temperature can increase the rate of enzyme reaction, I mean, as long as you don't go so far that you denature it, is because temperature will increase kinetic energy. It'll cause those molecules to move faster, and kinetic energy of either the enzyme or the substrate or both causes a greater chance of that collision occurring. And then here's just a fun example of how immobilized enzymes are used in milk. They're attached to an insoluble material or membrane. That way it's convenient to be able to reuse the enzyme and not have to have it be like grody and weird in the food. All right, so let's look at molecular motion. And so you see we have our water molecules. Let's color them blue. And then we have our substrates and our active site. This is water. It's blue because it's water. Boop, boop. Let's change the color of substrate so that I have a highlighter that matches it. We'll make substrate purple. I think it would drive me slightly batty if I had to keep coloring in things with a pen. I should have also used the other side of this highlighter. Oh well, too late. We're already in motion. And then our enzyme. I really do like enzymes being red. This is like big lumpy fella. And then active site, I feel like has to be yellow. Yellow or orange. There we go. That's the active site. Oh, now I can't highlight the word. No. Yeah, no. It's fine. I'll just make the arrow more obnoxious. Be better than me. Highlight active site before you color the enzyme. Alrighty. Decoration aside. So your molecular motion is really just the idea that movement is needed for these collisions to occur. So your enzymes and your substrates are mobile, kinda. So enzymes kind of. What color is the substrate now? Purple? Oh, let me use the other purple. That one's hard to look at. Let me get the black ready. And substrates are mobile. Which just means that they can move around. And so collisions between the molecules will occur if they're mobile. And they all will occur in an aqueous solution, because even in the membrane, remember your membranes are in your cells or in some sort of solution that has cells in it, and so they'll all occur in some sort of water-based aqueous solution. We'll use blue to write aqueous solution for funsies. But this aqueous solution and just being in a liquid in general enables or allows continual motion of the molecules. The only caveat to this, you're like, oh, Miss White, they're constantly moving. Of course we're going to have constant reactions. That movement is completely random, and the direction is constantly changing. So this motion of the molecules is completely random. And constantly changing. So the chance of the substrate binding to the active site on the enzyme and this reaction actually occurring is also kind of random. Higher concentrations of enzymes or higher concentrations of substrates will help increase that rate of reaction, but ultimately it is going to be kind of a random process, which is true for all molecular reactions. Oh, and to readdress this little asterisk here, excluding immobilized, membrane-bound enzymes. There we go. And so we have this movement happening because they're in this aqueous solution. They're constantly moving. It's random. And so due to the random nature of it and the changing direction, there are other barriers. There's ways we can help improve it with speed of movement. And then there's also some barriers to this process, like correct angle and alignment. I feel like angle is not spelled right there. Maybe I'm just crazy. I think I'm just crazy. And so with your angle and alignment, if your active site, which I'm going to write it in orange because writing in yellow that's not going to show up. So if your active site and the binding location on your substrate, I guess if active site and binding location on substrate or binding area on substrate are not aligned, collision can occur. So like they will still hit each other, they will still bump into each other, there's still two 3D objects clapping together. but may not cause reaction. It's like if you tried to put your key in the keyhole, but you tried to put it in with like the fatty part of your key forward. By the fatty part of the key, I mean like this part. It's like if I were to go to unlock my door and I stuck my key in like this, it would still hit the lock, but it's not gonna go in there at all. You'd have to put it in the correct way. So this would be like, okay, here's the, oh, here's a lock. Here's the keyhole. Here's a lock. There's the keyhole. This way, we're sticking the key in the normal human way. Boop, 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 boop. Teeth first. This way, we're sticking the key in fatty part first. Boop, 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 boop. Why would you do that? They're still gonna touch, but nothing's gonna happen because that orientation isn't right. In this case, on your enzyme, A boop, 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 has to hit B. B will make the purple one, so that's the binding area. Oh, and you know what? Because C is not going to bond, we'll make it the doo-doo brown highlighter. Haha, loser. I'm having too much fun. Can you tell? And so, orientation correct, yes reaction. Orientation incorrect, no reaction. And then where's green? Oh, la 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 la. Yes. All right, and then last up, speed of movement. E. Substrates are typically smaller. Oh, where's the black one? Which means that they will move faster. I feel like faster needs a color too. We'll make faster this one. Move faster. Think about like a tiny little mouse running versus like a big, I don't know, a bear. Bears, I guess bears run fast. I don't know. And then if we have more movement, it gives us more collisions, or more collision chances. Which gives us bump-ba-da-dump, more reactions. And speed of movement, I think we'll talk about it when we talk about temperature, but speed of movement for like molecules and particles, higher temperatures have higher speeds of movement. It's typically due to higher kinetic energy and smaller size. I guess we should add that in, right? Yeah. Higher kinetic energy equals more speed. Zoom. Think about like when you have a sugar rush and you're like bouncing off the gosh darn walls because you're full of energy. Yes, same with particles. All right, this page makes me mad. This page, I put these to Copies Plus. This page uses the same gosh darn simulation I tried to have us do in class that doesn't work. So unfortunately, exit. We can't do it. I'm sorry. It makes me upset. Same with the top of this page. It's for the same thing. Exit. Can't do it. MCPS said no. They said, Jessica, sorry. Kids don't get to know about it today. Rude. But down here we can actually look at denaturation. So, bump it up. Like we talked about denaturation with proteins, guess what? Fun fact, if you didn't know, enzymes are proteins. Woo! And so their structure can be altered by changes in temperature or pH. Doesn't matter. Either one. Oh, let's give temperature and pH a color now. I feel like temperature is giving whatever this color is supposed to be. And pH can be, I don't know, green? Sure. And so if changes in temperature or pH happen that are too far outside of the optimum, for pH, it depends on what the specific enzyme is. For temperature, it's typically high temperatures. Cool temperatures will just slow down molecular speed. They won't actually denature that enzyme because it's not adding energy to break those bonds. But either way, if those two parameters are offset from what they should be, the shape of the active site is changed considerably, and the enzyme is said to have become denatured because it won't function anymore because that shape has changed. Active site is changed considerably and is said to have become denatured. Oh, shape of the active site. We already know how important that shape is. It's so important to the point where it kind of Play-Doh-y bends. So if it's like all out of whack, even if it tried to Play-Doh-y bend, it's not going to happen. Not going to work. And so if we look at these, you can see that the ones that have really malformed shapes, these are our denatured ones. And so this one denatured, oh, I should have done this with the temperature color. Oh well, it's fine. And then this one denatured by, I'm assuming a pH change. They're going with urea. And pretty much all of these ones are way out of whack. And so this one is at a different pH. This one is at different temperatures. This is at a higher temperature, normal temperature. And then this one is just like standard. And so you can see the shape change as the conditions change. This one's arguably denatured, but it's fine. And then it has your little descriptions down here. So high temperatures can cause denaturation because the extra energy leads to increased vibration within the molecule, breaking the bonds within the protein. Oh my god, my nose is bleeding. Okay. Well, let me finish this page, and that's it, because my nose is bleeding. Why? Why do they do this to me? I'm going to finish this page, though. Changes in pH lead to a higher or lower concentration of hydrogen ions in the solution. As a consequence, hydrogen bonds within the enzyme are broken, causing it to change shape. All right, my nose is bleeding. So, yep, that's as far as we're going to get today.